a tree, which you get by taking a certain pre-image of a point under the dynamical system. You get a Galois representation, which maps into the automorphism group of this tree. That representation, it's not quite true that it has finite index if and only if the point is not post-critically finite parameter, but it's almost true. Okay? So work of mostly Pink and Jones gives a more convincing analogy. Okay, but it's a little technical, so let's skip it. Okay. Alright. So, my claim here, and I left these things up here, of course, for this particular purpose, is that PCF points are actually analogous to CM points. And so you could certainly at least make the same conjecture that you did for elliptic curves. Now, maybe it's true, maybe it's not. But we can write it down. So this is a case of dynamical Andre Oort. And that is, you could conjecture that if we consider products, so pairs of rational maps that are polynomials of degree 2, so now I'm restricting my attention to this family here. So consider the affine 2 spaces parametrizing pairs of these things. projection locus of the family z squared plus c is the boundary of the Mandelbrot set. Okay, so what is the Mandelbrot set? If you recall, I said that there was a dichotomy in the shape of the connectedness of the Julia set that depended on whether the critical orbit of a polynomial was bounded or not. Okay? The Mandelbrot set is defined exactly this way. It's the collection of parameters such that the critical orbit is bounded, or equivalently, the Julia set is connected. Okay? So what does this thing look like? So I didn't even bother putting a picture on the slide because we've all seen pictures. So this is this sort of complicated guy, and you can tell that it's complicated because of my little tendrils here. So the Mandelbrot set lies inside the complex plane. It's this collection of parameters under which the strategy of the proof is due to Baker-DeMarco. And it again, as with the classical case, consists of two components. Okay? So first, the bifurcation locus at the boundary of the Mandelbrot set, somehow if we have a plane curve here that has infinitely many special points and is not of type A or B, we'll have properties that are both transcendental and algebraic. Okay? So the first part is the algebraic part. So the first step is to show that such a curve, if C has
temporal loop model can be extended into modern cosmology in several different ways, accounting for some of cosmology's unanswered questions.
Caltech professor Fritz Zwicky looked up to the neighboring Coma cluster of galaxies and observed something strange.
He could estimate the size and then obtain the mass in the cluster, and he found that it was vastly more massive than accounted for by the luminous matter.
Something didn't add up. The galaxies were moving too fast within the cluster for the amount of illuminated stuff he could see.
The subject remained dormant till Vera Rubin and Kent Ford measured galactic rotation curves.
Like Zwicky, her observations also seemed strange.
The only way to resolve this paradox of galaxies which spin 10 times too fast is to assume that there is a halo of invisible matter surrounding the galaxy, keeping the galaxy whole.
If this is a galaxy viewed edge-on, and you measure the velocity of gas going around the galaxy,
the gravitational acceleration due to a mass at the center would be m times g divided by the radius squared to the star, and that has to equal the acceleration, and the acceleration is the velocity squared divided by the radius. So this would then say that the velocity falls off like 1 over r. This is Kepler's planetary law. It's usually expressed in terms of the period rather than the velocity. Velocity falls like 1 over square root of r as you move away. That's not what was seen by Oort, and it's not what's seen by anybody since. What was seen is that the velocity is pretty much constant. Not the angular velocity, incidentally. It's not like this thing is rotating like a big giant pinwheel, but the linear velocity. The linear velocity appears to be constant. So instead of saying all the mass is at the center, let's say the mass is distributed, and let's introduce a function m of r. M of r is the amount of mass contained within a sphere out to radius r. Not of a constant mass at the center, but a varying mass which varies like m of r. And in that case, v is constant, doesn't change with distance, and therefore we find that m of r must grow like r. M of r increases as you move away from the center, and so as you move out, this is not the mass density, incidentally, this is the total mass within a radius r, apparently increases linearly with r out to the outer boundaries of a galaxy, and even At the moment, it looks like a piece of luck that the velocity curve is just flat. And I don't know a good, substantial, simple argument about why that's the case.
Three-dimensional time can be used to account for the anomalous rotation curves of galaxies without appealing to the presence of dark matter. The expression used in Susskind's example, where mass is a function of the radius, could be used in an alternative way to mathematically argue that there is an increase in the passage of time as the radius increases. For simplicity, we can substitute the basic temporal definition for mass with m, letting the variable n equal 1 for simplicity. Since we are dealing with a change in the passage of time relative to a gravitational field, as opposed to dealing with some mass, we can drop the minus sign. Since the t² term is proportional with the units for g and v², only the passage of time term can vary. Therefore, the passage of time can be a function of the radius such that the passage of time increases with the radius consistent with Einstein's equivalence principle. This tells us that the relationship between inertial mass and gravitational fields can remain consistent, while the radius as a function of t prime varies with the distance from the center.
Dark matter's invisible presence is everywhere, or so it seems. Science has not directly proven dark matter particles exist.
If time is really three-dimensional, affecting our observations of distant objects in space, then we really do need to take it into consideration. Using the temporal 4 vector, we can see that there's one space component to 3 temporal coordinates. Recall what each temporal component corresponds with, and how they relate to the temporal definition for mass. As t squared, or linear time, extends, both the period and present time components extend such that for any given moment, the slope between periods to present moments is 1. In this case, both the passage component and the mass are unchanged. The net effect of this is that the mass can be set over a single spatial coordinate for an extended period of time, such as a point particle mass. If we extend that spatial coordinate into being a vector of three-dimensional space, then that point particle mass can be spread homogeneously over some volume of space as well. In an odd way, the mass is in more than one place at the same time, even though that same mass is in the same place at more than one time. If we examine certain images taken of gravitational lensing, a familiar geometry comes to mind: Lagrange points.
It's helpful to think about these things in terms of where you want to put satellites into orbit. Then a geostationary satellite just stays directly above the same point on the Earth because it's going around at the same speed as the Earth is rotating. But there's a subtlety here. What you're actually doing is a three-body problem. You've got the Sun, you've got the Earth, and you've got your satellite. And so the force that you have to think about isn't just the force of the Sun, it's the force of the combination of the Earth's gravity and the Sun's gravity. At this point, if you think about what the pulls of gravity is doing, the Sun is pulling you that way, the Earth is pulling you that way. So both of them are tugging you in the same direction. So the net force